Good day, everyone. Myself, Md Atikur Rahman. Uh, Today, I'll be talking about my topic of the presentation is waste to wonder how I converted this Borassus husk fiber reinforced composite for sustainable engineering structure or application. To get into this whole presentation, I made the presentation or derived the presentation into some sub-segment or section. First, I'll be talking about the tree itself, Borassus flabellifer tree, followed by biofibers in modern engineering applications, then method used in this particular research, properties of Borassus husk fibers, both at its treated and untreated condition, and then we'll look into its composite reinforced epoxy, and then finally see the summary and followed by the last segment is the references. So the tree itself, Borassus flabellifer, this is one kind of wandern tree in our region, we say that. So in Asia, this is known as Asian Palmyra palm. It's a key crop in South and Southeast Asia, producing fruit and palm sugar. They are actually very common over there. Followed by its trunk, which is around 30-meter long, used in building and furnishing. Its roots can go beneath the earth around 15 meters down vertically, and that's why it can retain soil, soil erosion even. It has high chlorophyll stability index and relative water content. That's why it is a drought tolerant and it can be planted even at higher altitude, at even diverse temperature zones 0 to 45 degree. The fruit pulp, which is the perhaps the most common uses we have seen, is generally used for preparing foods. And also some of the other cases we found in Indonesia, they use this one for medicinal purposes. And the fruit shell, which is my actual research material, generally we use this one for agricultural waste and to use as fuel to for cooking in rural Bangladesh. So let's see some of the biofibers are used in modern applications. Um, First, we can see this one. There's a Airbus A320-200 wing box was constructed using Remi fiber-based composite, and that was been able to reduce the weight around 14%. The flax reinforced polymer that was used in tailplane, cabin door, partition panel, and some other um, internal structures of the aircraft. And this is quite fascinating. In 2024, first wooden satellite, Lignosat, which was made of Honoki wood. This wood is, by the way, is based on Japan, and that was the first leap of this biofiber to advanced engineering application. And this is the car parts. We all have found that like BMW, Mercedes, Porsche, they introduced biofiber-based composite from hemp, flax, and sea cell for dashboard and all the internal structures. So inspired by these one, then we actually go for this particular research. And for the research purpose, we'll show first how the fiber extraction from the food shell we have done. You can see in the image, that was the actually shell. And when we cut this one with a hammer or even knife, we can see we take out this white portion, which is a little bit edible portion, and that's the leftover thing. We use leftover this shell for a cooking purpose back in our country, Bangladesh, or maybe agricultural waste. Now, what I did, as because when I see the fiber is non-uniform in diameter, that's why I crushed this one to a powder so that we can use this one. And you can see that one in the image. Then, after the powder, because we know those biofiber is covered with all those pectin, hemicellulose, and wax. So I need to take it out. And this is the treatment we do, alkali treatment. There's a lot of treatment, chemical treatment can be done. But for my research, I have done the alkali treatment. And after the alkali treatment, you can see the image over there. It's a bit darker. And that's the reason for that. It actually removes the hemicellulose, loose lignin, pectin, and the surface become rougher, which is good for the adhesion, further adhesion property. For our research, I used distilled water, sodium hydroxide, and fiber into a ratio 19:1:1. And the treatment time I use 0.25 hours. That's been 15 minutes to 2 hours. We need to be mindful that if we put it down for a longer time for the treatment, that will be detrimental for the fiber. And we'll see that for one. So that's an image. You can see that. So then we'll see the resultant discussion after all those things. So stage out 1 and 2, we have done the uh, testing for untreated and alkali treated fiber, and this is based only on the fiber itself. So what the test we have done, we did the physical properties, mechanical properties. I put it down into this color because that is we have done for untreated fiber. When we got good values, then we did the further chemical analysis, morphological properties using ACM, and then thermal properties. And those are the cited 1 to 3. Those are the published article already been enclosed into the reference section. Physical properties. That's the physical properties. Pretty fascinating. We saw everyone. We saw that the fruit is floating on the water, and from that indication, I got the feeling like it should be lower than the density of the water. That's why it's floating. And yes, we figured out that value. The density I found 0.74 gram per centimeter. By the way, these all tested have been done according to the industry standard and followed by other researchers' methodology. And the water absorption, it was below 50%, and porosity around 35%, and moisture regain around 4.5%. So when we are convinced with that, we did further the mechanical properties. Now, probably you have seen that. I did not include that image over there. Probably if you go back to my article number 2, which I put it down inside the reference section. This is a carb beam actually. This is the first time we are the first done this carb beam test on the biofiber. So we've tried to figure out the interlaminar tensile strength from the 4-point bending, flexural bending, and that's a carb beam. And we found that 4.16 is a megapascal, its mean value. That is also adhering the standard. And then, as because that calculation is a little bit complicated, adhering the anisotropy beam theorem, then we did the short beam test, which is pretty easy through a 3-point bending, which is pretty conventional as well. But there is a limitation for that. So we found that 7.55 megapascal. So these are actually convincing results that gave us like a hope we can go further. And then we did the chemical analysis, which is combination of untreated and treated fiber altogether. And you can see that I precisely marked 2 points. Those are 1741 and 1255 web numbers are. So those peak are actually representing the presence of hemicellulose, and you can see that is in the untreated. However, when we did the treatment, all the treatment, this been replaced. That's been with the treatment, we significantly were able to reduce the prevalence of the hemicellulose, because hemicellulose is too hydrophilic. So because of that, it absorbed water or moisture, and it deteriorated our thermal and mechanical properties. And after the chemical analysis, we did the morphological analysis, and that's even clearer to you. You can see the left-hand side, that's the untreated fiber, and on the right-hand side, that's the treated fiber. After the treatment, all those pectin, debris, and wax been taken out, and that's why the fiber surface become rougher, and that rougher surface is good for the adhesion, enhancing the adhesion property. And when it is hemicellulose has been taken out, only we have left over with cellulose and lignin, and those are actually contributing for thermal and mechanical properties. So when we are convinced with that, then we did thermal properties test through the thermogravimetric analysis, TGA. And you can see I marked 3 places in the graph, A, B, and C. That A is the presence of moisture, B is the presence of hemicellulose, and C is the presence of the cellulose itself. So we can see that only the untreated fiber has those three distinct peak. When we did the treatment, after the treatment, all those hemicellulose been gone. That's why there is no distinct peak over there. So this is another way to prove that that after the treatment, hemicellulose been gone. And another interesting thing you can see that, I mean, when it is untreated, the weight loss rate is higher maximum. With the treatment, it actually reduced. So with the weight loss rate is higher, there is a connection between its thermal enhanced thermal property. So we'll see that then we take that value into a table. So I did not enclose all those value over here. The article already been published, so those are like cited over there. So we can see that when it is untreated, the char residue were 21%. When when we treated that one, it actually increased significantly. However, as I told you before, with the prolonged treatment, there is a distinct probability that cellulose would be um, damaged, and therefore the value for 2 hours is down. It's going to 25%. IPDT, that's an interesting property that was first introduced by Doyle in around 1961 or 65. That means this value actually encompasses the whole graphical situation or the scenario of this thermal properties. And because this biofiber is composed of hemicellulose, cellulose, and lignin, they have all three composition have a distinct thermal characteristic. So it's like anisotropic. So this IPDT explicitly express the holistic nature of the material, and if it is like some kind of anisotropic material. Anyway, for our test, we found that this value is like a consistent or proportional to the char residue value. And there's a integral process decomposition heat flow or heat, IPDH, that was introduced by me. So with that, we can figure out how much heat been absorbed or rejected during this scenario. So the minus value refer to that it been absorbed, and that's because of the uh, presence of the hemicellulose. And with that value, by the way, we can even predict what is the specific heat capacity of this material. And this is quite important for the anisotropic material when we have a like diverse heat capacity of the each component. So further, actually, we confirm this value with the DSC. Because DSC explicitly talk about the specific heat capacity, and that's why the DSC it is. We did the further confirmation for the DSC, and you can see that in the DSC similar thing. The red color is showing that untreated fiber, which I again marked three places: A, B, C. A is the presence of moisture, B is the hemicellulose, and C for cellulose. So for the untreated fiber, again, the B is big, prominent over there. That's been the presence of hemicellulose been there. And after the treatment, it been gone. Gone. So we'll observe that when you see the background of that, and with the value even, the hemicellulose got higher specific heat capacity value, followed by cellulose, and the final is lignin. And that's why when we did the calculation, we found that the untreated fiber got 1.6 joule per gram per degree Celsius. When it's been treated, the value actually dropped, because quite obvious, after the treatment, the hemicellulose has been gone. And that's already been proved from previous tested, whether it is chemical or thermal test, TGA tested. And that is one of the indication that we are even coming to the conclusion that the value I introduced in the IPDH through TGA, that is actually complementing this one. So yeah, after that, when we are convinced with the result for the fiber, then we thought we should give a go for the composite now. So the composite preparation, we used 10% weight percentage of the Borassus fiber with the 90% of the polymeric resin. And on this occasion, we used two different kinds of epoxy resin. One was conventional epoxy resin, which a low TG value plus transition value. One is the high heat resistant. So we'll see those things. And that's the whole layout of my composite preparation. We put down all the mixture into the mold. We keep those mold into the normal atmosphere or atmospheric condition for 1 day. and then we take out the mold and we put it down into the oven for at a specified temperature for curing. So depending on the resin, actually this curing method is different, and that is actually adhered by the technical data sheet provided by the supplier. So let's see that representative name for set 1 with laminating epoxy, EL2. We ordered this sample from the Easy Composite from the UK. So they are a supplier. So these are the name, quite a lot of name. So neat epoxy, NE, the shortcut I use. Untreated Borassus husk fiber reinforced epoxy, that's a EUB, H, and 0.25 hour, that's been 0.25 T treated actually. Then 0.5, 0.5 T, that's been treated Borassus. So these are the sample I actually marked for that. That is for the when set 1, and the set 2 composite that I use high heat resistant epoxy on this occasion. And EL 160, that's mean it has a higher temperature, glass transition temperature, which is 160 mean it's 160 degrees centigrade. So HE for the high heat resistant, and 0.5 hour alkali treated, 0.5 TB. But on this occasion, by the way, we did not include any untreated because we already got the untreated not so good results. So we just took it out. We just put it down, comparison between treated and base resin. This article, although these are published article, you can find it in the reference section for details. Anyway, let's give into go result and discussion section. So that's both for the properties of set 1, set 2 of Borassus fibre-reinforced epoxies. We'll see the morphological properties, thermal properties, thermomechanical properties through DMA, and then outgassing properties. From the morphological properties, when we use the untreated fiber, regardless of whatever the epoxy we have used, we found that after the breaking sample, the fiber being placed randomly inside the resin, and therefore after the breaking, we saw that the fiber being pulled out, and because of the pulling out, there is a void creation, and that is the indication of the not so good or poor fiber matrix adhesion property. And on the other hand, when we did the treated fiber with that, we got completely different scenario. We saw that the fiber been embedded inside the resin properly, and that's why instead of fiber pull out, we observed that the fiber break out, and because of that, that whole property will influence its thermal and mechanical properties, and this scenario shows that there is a better fiber matrix adhesion property or better interfacial bonding. And that's why when we did the thermal properties via TGA for the set 1, because it's a bit of the long list, and that is for the set 2. I will take you to the table graph, table section, which is better to represent. That's for the first set. So when it is neat epoxy for set 1, the char residue found 6.2%. Untreated, it enhanced actually 7.6% because of the inclusion of the fiber. Because the bio-fibre, it has inherently higher thermal properties, which we saw before. And after the treatment, treated fiber being incorporated, it's actually enhanced to like 10%, 10.1%. So it's quite of a good thing after inclusion of the fiber. And if you see that IPDT, of course, there has a very similar result. However, with the IPDH, we found that inclusion of the untreated fiber, the value, it become a little bit absorptive, heat absorptive, like the endothermic, and that's why the minus sign came up overall, and that is the indication that there's a presence of hemicellulose been there, and that's why it came out like that. And that's minus sign also indicating that as because hemicellulose has the higher heat capacity, we're expecting that from this sample that untreated fiber would have the higher specific heat capacity value. Now going to the second sample, where is the HE got the 5.7%, and all the treated fiber and for the 0.75 it's got higher. So this is the indication that with the high heat resistant or with the treated fiber, things become higher. Now there is a distinct difference about that. The normal neat epoxy that got higher UV resistant property compared to that high heat resistant property. They don't have that. They have the capacity of moderate UV resistant property, and those properties was confirmed by the supplier themselves. Let's get to that. Thermomechanical properties for set A via DMA, and you can see that the red color that is denoted by neat epoxy. So the glass transition temperature I actually picked up from the loss modulus, peak of the loss modulus. It was 84 degrees centigrade. However, the untreated fiber is 79, reduced. With treated, it actually enhanced to 95 degree temperature. So 95 degrees centigrade, sorry. So with the treated fiber, actually it enhanced at some point. However, for 2 hours treated, it actually reduced. And for 2 hours, it's a prolonged time. So a lot of cellulose being destroyed. So that's why the value dropped again. So, and then if you see that damping factor value, you can, so with the damping factor, we also figured out there is another new property we discovered, the phase angle. With the each of the vibration, material is shifting from one place to another. That's what the viscoelastic property we say that. The change of angle in between initial state to the later state, it defines how much it has capacity to dissipate energy. So for the net epoxy, we found that the damping factor value is 0.9, below 1 actually, and that's why, and that is reflecting in the phase angle change value, initial and peak of the loss modulus. And untreated, it got 0.9, pretty much similar. However, when it is treated, it becomes 1.2 because it has a better interfacial bonding. That's why it has a better capacity to dissipate heat or energy out of the system before it breaks. So this is one of the key property to numerically analyze whether or predict how whether it's a damping factor would be or impact property should be. And this is a similar test we have done for the set 2 sample, and that's the interesting result we found. Interesting result is that HE over here, the heat resistant epoxy got the highest TG value, which is 149. However, even though incorporating treated fiber, this value reduced actually, and that is the indication that biofiber got the limitation. Biofiber got the limitation. It should not be using like for high heat resistant application. They have a limitation, and that's the constraint we found. Pretty interesting, but that was also insightful. And when we convinced, when we see that is damping factor or impact properties, we found that the high heat resistant sample got the damping factor of 0.8. However, with the treated, it actually enhanced. Although its TZ value decreased, but it actually enhanced. So that's a good one of the good way we still can found. So we got the limitation, but we got a good sense of it. Then we try to compare all those values with the previously found value, and we can see that that's the untreated Borassus fiber epoxy, which our result, that's why I put it down in different color, pink color, 79 degree, and the damping factor are 0.91. What is the alkali treated Borassus husk fiber epoxy? We use EL2 and 2 different resin, and we got 95 and 140 degree maximum. Similarly, the damping factor was 1.21 and 0.96. Whatever we found in the, then we look into the literature, and we found that rest of the jute epoxy, Borassus sprout epoxy, knaf epoxy, those values was actually less than what we found. So even the damping factor. So that's why it's a bit promising result we found experimentally. Then we did the outgassing test. This test actually a unique test. This test we do when we try to see the feasibility of the material, whether they can be used in the space condition or high vacuum condition, those type of situation, especially for the low Earth orbit. I was actually inspired by a work by Japanese university for the LignoSat, I think, the very first place I talked about that. So that's why I investigate that one. So, but this was special because I did not use only single standard. I actually combined two standard. One is static and dynamic. That's the article actually. Number 7 article. You can investigate that for the further. So that's why I did added three different temperature condition: 130 degree, 135 degree, and 40 degree. And that is for the both actually. And we found that although we have the equipment limitation, we found that that value is below our set value. So we are expected, but I suggested that if we have the better equipment, probably considering the fact that we have the limitation over here, so we need to redo that one. But this is a convincing result we got. The total mass loss was below 1%, even though we baked or prepared the sample in a normal condition. So yes, after all those things, the summary we came up, that's actually the ending portion, I can say. The untreated fiber initially exhibited very promising physical, thermal, and mechanical properties compared to many other natural fiber which are found in the literature, such as jute, rami, and flax. And then there is with treatment, alkali treatment, precisely, hemicellulose has been removed significantly, and therefore thermal stability enhanced, and we saw the result. And we made two different set of composites, set 1 and set 2. Alkali treated fiber showed high thermal properties from the TGA compared to the base resins and other conventional biocomposites found in the literature. And with the DMA, there is a diverse result we got. For the set 1 sample, the alkali treated fiber got higher TG value, glass transition value, and damping factor value, exhibiting better fiber matrix adhesion property, and that was supported by the ACM. But for this set 2 sample, the DMA showed that the TG value reduced for the fibre-reinforced epoxy, although it is treated, but tan delta, or the damping factor value, enhanced for the biocomposite samples, indicating limited energy dissipation capacity at elevated temperature, although good fiber matrix adhesion property confirmed by the further ACM we found. And then with the outgassing result, that suggests that the total mass loss is at acceptable limit for both samples, considering the fact that the limitation of our equipment, and that was actually comparative to our what we found in the literature. And overall, all the actually experimental results suggest that alkali-treated Borassus fiber can be suitable for advanced engineering applications such as current aerospace and automotive structure, especially for the internal structure. And this whole concept, this whole project or thesis, actually research work, can promote the sustainable development in the engineering application to meet net zero target or carbon negative approach set by Paris Agreement and UNSDGs, United Nations Sustainable Development Goals. And I should thank you so much for your patience. And if you do have any question, please feel free to ask me, and that is my contact details. You can even contact me for any collaboration, any work, or any queries. From my understanding, from my work, I will certainly get back to you. Thank you.